Start over. Hi everyone. My name is Shreya. This is my Physics 2211 lab 4 on oscillations. So the purpose of this lab is to analyze the motion of an object, specifically a mass attached to a spring as it oscillates and swings in an arc at the same time. And then we wanted to compare the real-life movement of such object to a theoretical model in FlowScript. So to introduce some models, again, we have Newton's second law, which says that the net interaction between a system and its surroundings is related to its momentum. And we can use the velocity update and position formulas to look at its movement. And then also the energy principle, which says that energy cannot be created or destroyed, only transferred between a system and its surroundings. And then here's some relevant formulas, including the energy of the system equals the work of the surroundings, and then the potential energy for a spring and for gravitational, and then the kinetic energy formulas. And then here I've also included the force of a spring, and then that work equals the net force times displacement. So to give a preview of the results for this lab, we were able to find the period of oscillation in the x and y position for the object, and then we were able to find that the model does follow the energy principle. So for the initial conditions, you can see that our system is spring and the mass, and then gravity, and then our surroundings is pretty much nothing in this case. And then the mass of our ball is 0.402, and then I also added in the initial position and velocity vector, which are shown below. And then so for the details of this experiment, we basically used Tracker to analyze the movement of a mass attached to the spring in the video. I generated a CSV data file with the X and Y positions, and then I used GlowScript to create a model comparison between our real-world object and a theoretical model. So here's a tracker analysis. It's a little hard to see, but basically what I did is I tracked the movement of the object in Tracker as it was moving. In the video, and then I was able to generate graphs here on the right side and extract data from there. And then here's my GlowScript code. So you can see in the first snippet, I added the initial conditions for the ball, so the position and velocity vectors, which I took from my GlowScript analysis here. And then I then went on to add in the initial kinetic, spring potential, gravitational potential energy, and then the total energy, as well as L hat, and S. And then here, I went on to find the gravitational force acting on the mass, and then, which is just mg in this case, and then the spring force, and then so the net force is going to be the gravitational plus the spring force, and then I use the velocity and position update formula to update the position and velocity of the ball. And then we update L hat and S, which are used in calculating the spring force, and then I calculated the changes in energy below. So for the results, you found that for the X position, the period of the system is 1.71 seconds, and then for the Y position, it's 1.472 seconds, and then below is my calculation for this. So what I did was I found the period experimentally between two different locations on this chart above, and then I used two different periods, and then I averaged them together to find the experimental period. And I use this formula where t equals 2 pi times the square root of m over k, since and I was able to use that formula to then solve for my k values. And I did that for both the x and the y. And yeah, that's how I got my periods of oscillation. And then this question is asking, is the energy principle satisfied? And the answer is yes, because you can see here that this orange line is our delta E, which is our total energy, and that's pretty close to zero, which suggests that the sum of the potential and kinetic energies are zero, and there's no external work being done on the system. So, and then here's our graphs, so to compare the model to the experiment. So for the X position, we're definitely closer than we were supposed to be for the Y position. As you can tell, the model did not match the experiment very well in the second snippet. And I think this could be due to some sources of error, including the inaccurate placement of the tracker on the mass. And then also there could be work on the system due to forces like air resistance, so energy may not be perfectly conserved here in real life. Yeah, that's it.